All right, guys, let's go ahead and go over the warm-up questions. These questions you should have been able to answer based on the assignment that you did last Friday, or hopefully did the assignment on Friday of last week. With the energy exploration sims, you should have already taken some notes over these different forms of energy if you followed the directions that you were given. If you haven't yet taken any notes, then you definitely need to jot some stuff down today. If you did take notes, you can add to those because we're going to give you the equations for the different energy forms and go over some example calculations as well. So again, if you took notes on Friday, have those out in front of you for today's lesson. But before we get to that, let's go over the warm-up, and you need to make sure that you answer this in MyOpenMath. Number 1 says, what variables affect the kinetic energy of an object? And number 2 says, what about the variables, which ones affect the gravitational potential energy of an object? So let's do kinetic energy first. What variables affect the amount of kinetic energy that an object possesses? Mass and velocity, perfect. They're the ones in the formula, and we've used this equation before. We did it last semester, but our kinetic energy equation is 1/2 mv squared is equal to your kinetic energy. Therefore, mass and velocity, the variables that show up in that formula, they're the ones that have an effect on the amount of kinetic energy that an object has. So that's number 1. Number 2, gravitational potential energy is something that we haven't talked about yet, but it was in the simulation. What variable or variables affect the amount of gravitational potential energy that an object has? Height, mass. Now technically the equation does have a third variable in it. The equation for gravitational potential energy, which we'll talk about more today, is mass times gravitational acceleration times height. However, that gravitational acceleration on Earth is a constant value. Now, that said, if you were to find the gravitational potential energy of a ball on Earth and then do that same test on the moon, obviously you're going to get different values if you have a different gravitational field strength. Okay, but since we can't really change the force of gravity on Earth, and thus we can't change the gravitational acceleration of an object, then for the purposes of most of our calculations, we're really just going to be looking at changes to mass and height. But it is possible to talk about having different gravitational field strengths. You just have to leave Earth to do it. But please make sure that you have your answers for the warm-up submitted in MyOpenMath. And as I said, we are going to talk about energy today. And you do have an assignment, 902.1, that you can work on once we're finished with today's notes. That will be homework if you don't finish it in class. Okay, we're going to start with the definition for energy. And guys, we've talked about energy previously. We did it last semester in November or December, maybe a little of both. I can't remember when we started the unit, but it was toward the end of this semester. And we talked about kinetic energy specifically and work in that work unit, but with the kinetic or work energy theorem. But we did discuss energy very briefly because obviously kinetic energy is a form of energy. So as a reminder, energy is the ability to do work or to cause movement. Okay, it's the ability to do work or to cause movement. And objects can have different forms of energy. That energy is possessed by some object because it's not a tangible thing. But if you have, a ball flying through the air, that ball could have kinetic energy and gravitational potential energy, for example. And that are two different forms that we're going to talk about today. But your energy is always going to be carried by something. Oftentimes it's movement, but you could have energy of position, and we're going to talk about both of those today. Okay, so kinetic energy, this is the one you should already be pretty familiar with. But just as a reminder, kinetic energy is energy associated with an object's motion. Therefore, if your object is not moving, you will have zero kinetic energy, and you can see that in the equation Ke equals 1/2 mv squared. If your velocity is 0 and you multiply by 0, you get 0. And so the object does have to be in motion in order for it to possess kinetic energy. Looking at that equation, whenever we go to solve for the kinetic energy of an object, or if we're using a kinetic energy to solve for one of the other variables, keep in mind the units that you have to use. masses have to be in kilograms, and velocities have to be in meters per second. And that's because whenever you plug in those values, in order for you to get joules as your unit for energy, those things have to be true, because a joule is a kilogram meter squared per second squared. Okay, it's a lot shorter to write joule, but in order for you to get that unit, or if you're trying to cancel it to solve for one of the other things, you do need masses in kilograms and velocities in meters per second. Calories, I mentioned as another unit. It is not a unit that we will use in our calculations, but it is one that should sound familiar from your chemistry class for most of you last year. All right, so warm-up question, I asked you what factors affect kinetic energy, and this was our answer, mass and velocity. Okay, but you need to know not just that they affect it, but what the relationship is between mass and kinetic energy, or between velocity and kinetic energy. And this was something else that was already presented in the simulations on Friday, along with the notes that were embedded in there. You need to be able to figure out not just the relationship, but also what it looks like graphically. So you might want to sketch these out. We've been talking about these types of mathematical relationships all year long, so this is not new. But some of you are still struggling with it. So mass and kinetic energy, let's start there. If I were to double the mass of an object, how would its kinetic energy compare? Or if I just, let's say, threw two balls at the same speed, but one of them has twice the mass of the other. Okay, you should be able to do a comparison. And so if you look at that, if you were to have double the mass, looking at the equation, if you double this value, it should double your energy as well, because they're directly proportional to one another. Okay, and so if mass doubles, kinetic energy will also double. It's directly proportional, and a directly proportional relationship is going to look like a linear graph, a straight line like this. However, you don't get a straight line for velocity, and that's because it's not directly proportional. If you look at doubling velocity in the equation, if you were to double the speed that you throw the ball, but you kept the same ball, let's say, if you double the velocity, it doesn't just double kinetic energy, because in the equation, velocity is being squared. So if you were to double the velocity, you would have 2 squared, or 4 times the amount of kinetic energy. That's because this is a squared relationship, and you get a graph that looks like a curve because it's exponential. It is squared. And so as you increase velocity, your kinetic energy is increasing by a squared factor because of this equation right here at the top. So again, be able to answer questions involving proportional reasoning as well, or what those relationships are, or what they would look like on a graph. Let's try an example calculation now. It says an object has a kinetic energy of 52 joules and a mass of 13 kilograms. How fast is the object moving? So again, label the stuff. I've got kinetic energy and mass up there. I'm looking for velocity, and obviously I'm going to use the kinetic energy equation because that's the information that I have. Kinetic energy equals 1/2 mass times velocity squared. If I substitute in, that looks like this. 52 equals half of 13 times v squared. Now half of 13 is 6.5, and so I would have 52 equals 6.5 times v squared, and then I would have to divide both sides by 6.5. So you get this, 52 divided by 6.5 equals v squared. 52 divided by 6.5 is 8. That is not your answer, that is v squared. So the square root of 8 is approximately 2.8 meters per second. So again, if I give you 2 of the variables, you should be able to solve the third one in the kinetic energy equation. And your units for your velocity will be in meters per second when you solve. All right, so that's kinetic energy, and that was a real quick recap because we've already done it. We did it already last semester. You also looked at it again on Friday. So let's talk about the ones we haven't talked about yet. And those are our forms of potential energy. So potential energy is going to be energy that an object has due to its position relative to something. Depends on the type of potential energy we're talking about. I've got 4 different types listed up here, but in this unit, we're only going to talk about the first 2. Now, we will later on in the year also talk about electrical potential energy, We don't talk about chemical potential energy in this course, but you would have looked at it at least some in your chemistry class. But for this unit, we're going to talk about gravitational potential energy and elastic potential energy, both of which are still forms of energy and therefore have the same units, joules. So let's talk about them one at a time. I'm actually going to talk about elastic potential energy first. Okay, so first of all, this is sometimes called spring potential energy because a lot of times in the questions you'll see it has to do with a spring. It's going to say a spring has been compressed or a spring has been stretched by whatever amount. Okay, and so you may see it referred to as spring potential energy, but it can be any elastic object. It doesn't have to be a spring. It could be a tennis ball, like in my little animation up here. This ball hits the ground and compresses, and when it does that, objects, when you squish them like this, want to return back to their normal shape. There is a spring force pushing back outward to return that ball to a spherical shape again. Okay, and that's the same idea with a spring. If you compress a spring, the spring pushes back because it wants to return back to its normal shape, okay, or length in the case of a spring. And so if you compress or stretch an object, you're going to give it potential energy, specifically elastic potential energy. So again, the description says an object's energy resulting from compressing or stretching of an object. Because when you do that, that means now that you have this ability to do work because you have this force that's now going to get applied to return it to its normal resting position or length. The equation for elastic potential energy is 1/2 kx squared, where k is known as the spring constant and where x is the amount of deformation of your object. How much did it get compressed or stretched by? X is also called displacement. Okay, I just don't want you to mix it up with going a certain distance, but it is the displacement of the spring or the ball or whatever from its normal resting length or its normal shape or whatever. So EPE, elastic potential energy, equals 1/2 kx squared. Now K, the spring constant, is not like the constant we saw in our last unit where it's always the same number. It's not like it's always going to be 6.67 times 10 to the negative 11th, like our gravitational constant. It's not like that. However, it is constant for that specific spring. So no matter how much you stretch or compress whatever spring you have, if you have the same spring and you're stretching it twice as much, your constant's constant for that spring. And you can compare springs to each other when they have different spring constants because it tells you how loose the spring is, how easy it is to stretch it, or how difficult it is to stretch it. We'll talk more about that in a second. Okay, now I will point this out, and I did highlight them here, but your spring constant is typically in units of newtons per meter because it's the amount of force, newtons, that it takes to stretch it per meter. Okay, so how much force does it take to stretch it? So that's why I said it's basically the looseness of the spring. How easy or difficult is it to compress or stretch that spring? Your deformation, the units here need to match. Now they do need to be in meters for your calculation here at the end if you're solving for elastic potential energy because you need that final unit to be a joule. Okay, so you need Newton meters, which means if they're not in meters, you will need to convert because sometimes you will get a spring constant in centimeters or newtons per centimeter, or more commonly you'll get a deformation in centimeters. So just double check and make sure that everything's in meters or newtons per meter. All right, so again, factors affecting elastic potential energy. The main one we talk about is the amount of deformation or the displacement. How much do I stretch this spring? Okay, if I double it, if I stretch it twice as much, what happens? Okay, and if you look at the equation, if you were to stretch the spring twice as much, or compress it for that matter, it doesn't matter. If you were to cause the displacement to be 2 times as much, okay, what would that do to your elastic potential energy? And again, this is a squared relationship because the equation says 1/2 kx squared. The x is squared, so if you were to double your displacement, you would get 2 squared or 4 times the elastic potential energy. Spring constant, since it is constant for a given spring, we obviously can't talk about like the same spring. Hey, if I double the spring constant of this spring, because that's not possible. But you could compare two different springs and say, okay, I have this spring that has a spring constant of 100 newtons per meter, and this one has a spring constant of 200 newtons per meter. How do those compare? And you could absolutely do that. And looking at the equation, although it doesn't say it on my screen right now, if you were to like double your spring constant, for example, that would double your elastic potential energy, because it is a directly proportional relationship. But you'd have to compare two different springs. So that's why I didn't put that relationship up there. All right, so I mentioned this already, but since we do have a spring force, let's go ahead and talk about what that is. Since that's the force that's causing that object to return back to its normal shape, that's giving it that energy, we need to know what it is. So spring force is the force exerted by a compressed or stretched spring upon any object that is attached to it. The force tries to return the spring to its normal position. And it doesn't have to be a spring. I can stretch a rubber band and it will still want to go back to its normal shape. Or we can compress a ball when it bounces and it still wants to go back to its normal shape. Okay, but the spring force depends on the stretchiness of the spring, which is the spring constant. How stretchy is it? How loose is that spring? Or how difficult is it to compress or stretch it? Okay, that's your K value. The equation for spring force looks like this. Negative F sub S equals K times X. And in this equation, K is your spring constant, X is your displacement. And that force shows up as negative because it's always opposite whatever you're doing. Like if I'm compressing a spring by pushing it to the left, that spring pushes back to the right, opposite my direction. Okay, same thing if I were to pull it to the right, it's going to pull back to the left. And so that's why it shows up with a negative sign here. It's a restorative force. It always wants to return back to normal displacement or position rather. Okay, and so these are the same variables. So the reason I'm giving you this is because sometimes I don't tell you, hey, the spring constant is this, the displacement is this, find the elastic potential energy. I might instead say, hey, the force is this, and the spring constant is this, and then you'll have to figure out the displacement so that you can then solve for elastic potential energy. So it's possible to have two steps in your calculation if we bring in this equation here. So you might want to, again, add it to your notes. Okay, so talking about spring constant, again, I told you it's basically how stretchy or easy to stretch, loose, tight, whatever word you want to use, that spring is. And so this spring constant K is typically measured in units of newtons per meter and expresses the amount of force required to compress or stretch that spring per meter. So however many newtons it takes per meter. Stiff or rigid springs will have a large K value. Loose springs will have a small K value. So here's an example just to get you thinking about it. It says, if the masses hanging on each of these are equal, which of the springs below has a larger spring constant? So look at the picture, keeping in mind that a larger spring constant right here, a larger K, means you have a stiff or more rigid spring that's harder to stretch. Which one do you think would be your larger spring constant, A or B? A, because if it's the same mass on each of them, A is obviously harder to get it to stretch out, so it has a larger K value. Now if I gave you numbers on this diagram, we could figure out how much it's stretched, we could do a calculation, and we could solve for something with that. Okay, but just making sure you understand what it means. Okay, so again, this one would have a larger spring constant than B. Another thing that you might see is you might get a graph like this and be asked to solve a problem, and you have to use the graph to get your spring constant. Okay, and the reason we use this graph, if you look at that equation I just showed you for spring force is K times X. Now if you rearrange this equation, K is equal to the force divided by the displacement. That's what this graph is, a force displacement graph. It says it's example data for a baby bouncer that has springs in it, where the babies jump up and down. Okay, and so it has different force values and different displacements here. If you were to take a look at this graph, what is the spring constant for the data shown in the graph? What do we have to look at if we want to find it? Well, look at the equation right here. K equals force divided by displacement. That's your y-axis divided by your x-axis. That is rise over run, which means you need to find slope. Okay, if you have a force displacement graph, the slope of that graph, if it's for something elastic, okay, the slope of that graph is your spring constant. Okay, so if you need to make a note of that, please do it. Because if you have a graph and it's talking about a spring or something elastic, the slope of that graph is going to be your spring constant. What is the relationship between the spring constant and elastic potential energy? I mentioned this a moment ago, but it would be directly proportional if you were comparing two different springs and one had 2 times the spring constant. It would also have 2 times the elastic potential energy if you stretched it the same amount. It is directly proportional. All right, let's try an example calculation. And guys, I would recommend that you write this one down. The kinetic energy stuff wasn't really new. Maybe you didn't have to copy that one, but this is new. So if I were you, I would make a note. It says a spring with a spring constant of 5.2 newtons per meter has a relaxed length of 2.45 meters. When a 0.59 kilogram bucket of water is attached to the end of the spring, stretching it, the stretched length of the spring is 3.57 meters. Calculate the elastic potential energy stored in the spring. Okay, so looking at the information that I obviously have a spring constant. They were kind and they labeled it spring constant of 5.2 newtons per meter. But there are multiple distances in this question. Okay, in my equation for elastic potential energy, which is what I'm solving for, I need K, which I have, but I also need X. And I've got 2.45 meters, that's a distance, but I also have 3.57 meters. Okay, so which value should I use for X? Okay, well, if you know what X is, that might help. Okay, again, it is the displacement of the spring. So look at my diagram right here. Your spring has a resting length, that relaxed length, and it says it's 2.45 meters. So that's this. The natural length of the spring is 2.45 meters. That's not what X wants. Okay, whenever you plug into the equation, that's not X. That's not the deformation. Okay, it also gives us the stretched length. So it tells us how far it stretches, 3.57 meters. That's also not X. X is how much it stretched by, not how long it is after it stretches, but how much longer is it than it was before. Okay, and so if you want to give me a value for X, it's neither of the numbers in the question, rather it's the difference between them. Okay, because it was 2.45 meters, now it's 3.57, find the difference. Now the question might say a spring is stretched by 0.57 meters. Cool, it gave you X. But if it does this, and it says the relaxed length is this, and now it's this, you have to get the difference. So my value for X, my displacement or deformation of this spring is 1.12 meters. All right, so we have K, we have X. We're looking for elastic potential energy due to that stretching that we just saw. Our equation is 1/2 kx squared, which is 1/2 times 5.2 times 1.12 squared. Half of 5.2 is 2.6. 1.12 squared is 1.2544. Multiply those two together, and you get 3.26 joules. Are there any questions about the calculation? No? I'm hoping y'all think these are pretty straightforward. All right, so that's elastic potential energy. There's one more form we have to talk about in terms of our different energy forms today, and that is gravitational potential energy. Gravitational potential energy is an object's energy resulting from its position relative to the Earth. In other words, how high is this object off of the ground? Okay, that's how you're going to get gravitational potential energy. And you can see that if you look at the equation. GPE equals mgh, mass times gravitational acceleration times height. Keep in mind, you still have to pay attention to your units. Your masses still have to be in kilograms. Your heights have to be in meters. If they're not, you have to do conversions. Little g, again, mgh, that little g is 9.8. We're on Earth. That's our gravitational acceleration on Earth. Okay, now typically we have written it as negative 9.8, and you're welcome to do that. However, energy is scalar. That means it just has a magnitude. It does not have a direction. The fact that that gravitational force is down and our gravitational acceleration is down doesn't matter for energy. Okay, you're not going to give me a negative number because of that. In fact, you can't give me a negative number here. It's scalar. Okay, so just a heads up, that's why I didn't put the negative sign on here, because when I go to solve for it, I really don't want a negative number. Energy is scalar. All right, units are still joules, so let's go ahead and take a look at the relationships between the variables. And again, this was the other warm-up question that you had, is that what's the relationship between height in GPE and mass in GPE? So again, if you were to double height, you would double gravitational potential energy. They are directly proportional to one another. Same thing with mass. Doubling mass would double GPE. Okay, there's nothing squared in this equation. There's nothing being divided in this equation. So whenever I look at the effects on the gravitational potential energy, all three of those variables are actually directly proportional to it. They would give you a linear graph. Now again, we can't really change little g unless we leave Earth, so we don't really look at that one much, but it technically is also directly proportional. But we can really easily compare objects of different masses, or we can really easily compare objects dropped from different heights or held at different heights. All right, let's do an example calculation for gravitational potential energy. It says, calculate the gravitational potential energy of a 15.8 kilogram object positioned 5.8 meters above the ground. Again, we know the mass, we know the height. We're looking for gravitational potential energy. They're not going to tell us little g. We already know that too, though. It's going to be 9.8. And again, I did not plug in a negative. If I did, which I could, I would still have to take the absolute value at the end. Okay, I don't want a negative value here. My energies are scalar. So 15.8 times 9.8 times 5.8 gives me a gravitational potential energy of 898.1 joules. Questions about our gravitational potential energy calculation? I think it's pretty straightforward. Hopefully you agree. All right, let's go back to some of those different scenarios that we were looking at, or that you were looking at on Friday. One of the simulations you did was the energy skate park, and this one I like because it shows multiple different energy forms while you're looking at the skater. This question says, at which position on the ramp does the skater have equal gravitational potential energy as in the position shown below? So compared to this image here, that's just below my question, which of these lettered options, A, B, C, or D, does he have equal gravitational potential energy? What do we think? Take a moment, look at it if you're not sure. Yeah, C. You're just looking for where his height's the same, because again, if you look at the equation, mass, his mass didn't change. Gravity, that didn't change. So it's just the height. As long as he's at the same height, he will have the same gravitational potential energy. All right, what about this question? Assuming he began at the top of the ramp, what forms of energy does the skater possess at this position? So if he started up here, he's moving down, he's right here, we just paused it. What's he have right there? What energy form or forms? Is he moving? What do y'all think? Garrett, would he still be moving at that point if he started at the top? Y'all did this simulation on Friday. Come on. What did you say, Austin? Okay, Austin, what do you think? Is he moving at that point? If he starts at the top and goes down the ramp?
Yeah.
Yeah, he's still moving at that point. Okay, because he hasn't reached back up to the top of the other side yet. Okay, if he starts at the top, he'll go down, he'll speed up, and then he'll, when he starts to go back up, start to slow down. But he's still moving at this point, so he still has kinetic energy, and he still has gravitational potential energy because he has height. So both of them. Again, y'all need to be able to answer questions like this. Make sure y'all are listening. All right, total mechanical energy. Another definition to write down. We talked about all these different forms of energy, all of them that we've discussed, kinetic, gravitational potential, and elastic potential energy. All three of those are actually different forms of mechanical energy. Mechanical energy is energy that is associated with an object's position or its motion. It's the energy that's available to do work. And so the equation, if you're trying to figure out how much total mechanical energy, it's just adding everything together. So it would be your total kinetic energy plus your total gravitational potential energy plus your total elastic potential energy. Now with the skater on the skate park, for example, on that last slide, there's nothing elastic. That's okay. You would just add 0 for that part. You could add together his kinetic and his gravitational potential energies, and you could still get his total mechanical energy. So you don't necessarily have to have all 3, okay? But you're going to add together whatever you do have. Now, a lot of times the question doesn't say he has 15 joules of kinetic energy and 27 joules of potential energy. It's not going to tell you necessarily the amounts of energy. Instead, it's going to tell you, here's his mass, here's his velocity, here's his height. And so what you often need instead of this is to substitute in the variables. KE is 1/2 mv squared. GPE is mgh. EPE is 1/2 kx squared. So if you have it in terms of variables, do that. Substitute in those variables and solve for each of those pieces and add them together. Again, you're still going to be working with joules. All right, back to our skater. Assuming he started from rest at A, so this image here, at which position on the ramp does he have the most kinetic energy? So again, take a moment. I'm going to call on one of y'all because some of y'all aren't listening like you need to. Take a moment to look at this. Talk to your neighbor if you're not sure, but where would he have the most kinetic energy? You have 23 seconds to discuss it.
Yes, sir.
I don't know if we need that much time. Y'all probably already have it. All right. Alexander, what do you think? E. Yeah, he's going to speed up. At E, he would be moving fastest. He hasn't slowed down yet because he hasn't started to go back up. You're fastest at the bottom of the ramp. Okay, what about where's his gravitational potential energy greatest? This one should be easier. A, yeah, wherever he has the most height. Okay, so he has the most gravitational potential energy at A and the most kinetic energy at E. Okay, if there is no friction or air resistance, how does the gravitational potential energy at A compare to the kinetic energy at E? Does he have more gravitational potential energy at A or more kinetic energy at E, or are they the same? They should be the same. Okay, they should be the same. Anybody know why? There's a name for why. Anybody know what it is? We haven't talked about it yet. That's okay. The law of conservation of energy is really what we're going to get to. So again, when you saw this simulation, you saw the bars and they were changing one to the other, but this total stayed the same the entire time. We are converting energy from one form to another, but we are conserving the total amount of mechanical energy present. Okay, so you should have seen that in the little bar chart out to the side. All right, I'm going to end today's notes with a video clip from, this is a former professor. I don't think he's, I'm fairly certain he doesn't work anymore. He's far too old. This is Dr. Lewin at MIT, but it's an amazing professor, so y'all listen up to it. If you get professors that are this good in college, you are extremely lucky. But he's going to do a demonstration for law of conservation of energy, and he's very dramatic about it at parts, and that's why he's so entertaining to watch. But I'm going to let you guys watch this, and then we'll talk about a couple things, and then we'll be done with the notes.
Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10, so 150 joules. If I let it fall, then that will be converted to kinetic energy. If I will let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic breaks the building. And that's the whole idea of wrecking. So you're using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line.
I told you he's dramatic. He's going to put his life on the line.
If I release that bulb from a certain height, then that bulb can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here.
As long as he doesn't push it, he's good.
I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0.
Slow motion.
Physics works, and I'm still alive. See you Wednesday.
He is still alive. He is 88 years old. I just looked it up. He is retired. But again, it's a great demonstration of law of conservation of energy because he's so entertaining whenever he does it. But again, energy cannot be created or destroyed. It is conserved. It changes from one form to another. And what he talked about was it changing from gravitational potential energy to kinetic and back to gravitational potential energy, just like the skate park. Okay, just like the little skater guy. We're going to come back to law of conservation of energy later. Today, I really just want you to focus on the rest of the notes on the different energy forms, and that is in your assignment 902.1, energy forms problem set. That is what I need you to work on for the rest of the period, and if you do not finish it, then it is going to be homework due by 11:59 p.m. tonight. If you have questions as you're working, please let me know.